Hi, my name is Bakshree Mishra, and I'm a fourth-year PhD student at the University of Illinois, Urbana-Champaign, advised by Professor Sarita Adve. Today, I'll be talking about our work, Minstrel, Application-Aware SLM Inference Optimization on Edge Devices. Large language models, or LLMs, have become household terms, unlocking exciting new use cases such as AI-assisted pair programming, AI image generation, video editing generation, text summarization, and so on. All of this is great, and it also comes at a great cost. These models are enormous, spanning billions or trillions parameters, and have very high memory and compute requirement. Thus, they need to be deployed on cloud. And what this means is every inference comes at a cost, and further is subject to network conditions, server availability. And also, it means that user data has to be exposed over the network to cloud vendors. An alternative can be small language models, or SLMs, which are orders of magnitude smaller in size, and these models are provided by multiple vendors such as Google, Microsoft, etc. These models are targeted for edge devices and support use cases such as on-device personal assistance, code completion, customer chatbots, document summarization, etc. SLMs provide the benefit of being available offline, and through the sheer virtue of local inference, data privacy as well. Now, there is a vast amount of research optimizing LLM inference in data centers. Now, the question is, can we apply these optimizations to SLMs on local devices? Now, SLMs being meant for edge devices, they also support different use cases from that of LLMs. So there is a unique opportunity and unique challenges for hardware and software co-optimization in this space. So in this work, we introduce Minstrel, a model for predicting SLM inference latency for edge devices. Using Minstrel, we evaluate applications and hardware expected for SLMs and draw some interesting insights. Further, we identify zones for optimizing SLM inference. So to start with, SLMs are transformers. So just like in LLMs, there are two phases for inference: the prefill phase for processing prompts and the decode phase for generating output tokens. We can visualize this as in the flowchart on the left. It is well known in the literature that prefill is compute intensive and decode is memory intensive. Research for LLM inference optimization in data centers follows the general trend of mapping prefill to larger, more powerful hardware and decode stage to less powerful hardware. There are also other optimizations such as batching to improve hardware utilization and throughput. It is tempting to apply similar optimizations for SLMs. However, SLMs for on-the-edge devices can have different constraints and application behavior, and we must keep this in mind before applying optimizations. So what are the different challenges and opportunities between SLMs and LLMs? To begin with, the optimizations must target different platforms, data centers for LLMs and local edge devices for SLMs. These edge devices can range from smartphones to laptops and desktops, basically local devices owned by the user. Thus, the metrics for optimization may also vary. For example, for data centers, throughput can be a very important metric to optimize for. For local SLM instances, there can be downstream tasks that are stalled or waiting for these inference results, so latency can be a very important metric. For challenges and opportunities, batching, for example, is an opportunity in data centers that serve multiple user requests, but there is low opportunity for SLMs running on edge devices. Further, data centers have the opportunity of having pools of accelerators, CPUs, or TPUs to map inference to heterogeneous hardware. Meanwhile, edge devices are resource constrained. As for the type of inference requests or applications, it can be difficult to predict for data center LLMs as they support a wide range of user requests. However, with limited and known applications running on a local device, it is possible to predict the inferences for an SLM. So, can we leverage this unique hardware and software characteristics for optimizing SLM inference? So, if we were to capture per application characteristics for SLM inference, what questions can we ask? Can we determine the prompt length? Further, is there any reusable prefix, like in the case for agentic applications or multi-turn questions? In which case, what would be the incremental prompt length? If we are expecting formatted outputs like JSONs, what is the expected output length? What metric do we want to optimize for? In this work, we assume we are optimizing end-to-end latency, which is important for stalled downstream tasks. One insight is, can we use prompt and decode lengths to capture complex system or application behavior? So with this, we propose Minstrel, a model for predicting SLM inference on edge devices. Minstrel is a hybrid empirical analytical model which estimates inference latency given prompt and decode lengths. We express the total time as a sum of prefill and decode times, which are linear equations depending on prompt and decode lengths. More detail about our model and assumptions are available in the paper. Please check it out. We derive the model parameters through extensive hardware profiling, which we conduct with different SLMs and various prompt and decode lengths. The goals of the model are, first, given different constraints, can we predict the latency, inference latency, and verify if a hardware satisfies the constraints? And second, given different optimizations, can we predict the impact on inference latency? We evaluate Minstrel on two local hardware, a desktop with the NVIDIA 3070 GPU, and a mobile device using a Jetson or an AGX. We evaluate using the Llama CPP framework with 5 SLMs, Gemma, Qwen, Phi, Llama 3 billion, and 1 billion. We run our experiments with prompt and decode lengths observed in SLM tasks. First, we study the impact of prompt and decode lengths on inference latency. We begin with fixed decode length. On x-axis, we vary the prompt length, and on the y-axis, we measure the inference latency in milliseconds. The crosses denote measured values, and the red line denotes Minstrel prediction. We observe that there's a linear increase in inference latency with increase in prompt length. Similarly, next we fix the prompt length and vary the decode lengths on the x-axis, and we observe a linear dependency of inference latency on decode lengths. So for the cases observed, inference latency showed linear increase in prompt and decode length, and we see that Minstrel did a good job of predicting the inference latency. Now that we validated the Minstrel model for predicting inference latency, we study the benefits of optimizing different phases. To begin with, what if we were to optimize prefill phase by 2x? We study two cases for a long and short prompt lengths, with the prompt lengths are denoted by the color bar on the right. We observe that there is a diminishing return on optimizing prompt stage or prefill stage with increasing decode lengths, and in fact, the benefits reduce significantly for shorter prompt lengths. Next, when we study the impact of accelerating decode phase by 2x for both the prompt sizes, we observe that the impact is maximal for longer decode lengths in general, but especially for the short prompt lengths, the benefits saturate even at shorter output lengths. So if we were to summarize these trends together, we observe that for various prompt sizes, there's a similar diminishing trend for benefits from prefill optimization and increasing trends for decode optimizations on increasing decode lengths. But can we find a predictable pattern here? If we were to take the maximum benefit observed by optimizing prefill and decode and plot them together, we observe this trend where for shorter decode lengths, there is some benefit from optimizing prefill, but after a certain decode length, decode optimizations dominate. We observe this trade-off pattern for all 5 SLMs evaluated on both the desktop as well as the Jetson. We can simplify this trade-off as in the plot shown on the right. We observe that the application space, consisting of different combinations of prompt and decode lengths, can be divided into a prefill-dominated P zone and a decode-dominated D zone. Thus, if we are able to identify which zone an application falls under, one can make very targeted system optimizations for improving the SLM inference. Thus, to conclude, in this work we introduced Minstrel, a model for predicting SLM inference latency. We evaluate Minstrel on applications and hardware expected for SLMs and derive some key insights. Further, we identify optimization P and D zones for improving SLM inference for targeted applications. This is an ongoing work, and we'll be happy to take any feedback or any questions.